Okay, so today let's talk about free body diagram. Free body diagram. Also, we sometimes refer to this as FBD, free body diagram. Okay, so what is this? This is the diagrammatic representation of a single body or a subsystem. So it is diagrammatic representation representation of a single body, or it can be also a subsystem. Subsystem, and it should be isolate, isolated, okay, from its surrounding, showing, showing, showing all the forces, okay, whatever the forces that are acting on the body. So it shows all the forces acting on the body, acting on it. Okay, so it is better understood with an example. Okay, so let's start with an example. Consider we have a horizontal surface, okay, horizontal surface in which a mass m is resting in this way. Consider this object to have a mass of m. So, and this body is not moving, so we can call it, we can say this body is in the state of equilibrium, okay, equilibrium. So equilibrium. So, but even though if it is not moving, or we can say it is in the state of equilibrium, we cannot say the net force, the force, there is no force acting on the body. Net force will be zero, of course, because there is no motion here. Okay, net force will be zero, but there will be some force which will be acting on this body. Okay, so first of all, we know if there is some mass, there will be always some gravitational force which is always acting downwards. Okay, so downwards in this way there will be the gravitational force, and perpendicular to the surface there will always be a normal force. This is your normal force and this is your gravitational force. Apart from that, there is no force in your x direction. Okay, so only there will be the force in y direction. In negative y direction there is mg, and in the positive y direction there is n. So if the body is said to be at equilibrium, so then we can say the summation of the force in x direction is zero. Why? Because you see there is no force acting in this x direction, and and in y direction also force is zero, because the body is at equilibrium. And then if I write the equation for Fy from FBD, you will see the normal force is upwards and the mg is downwards. So I am using a negative sign out here just to show that these forces are opposite in direction. Okay, so and we know the summation of Fy is 0, so which makes our n minus mg equals to, so we which makes n minus mg equals to uh, which makes n minus mg equals to 0. So here n will be equal to here mg. This equation we derived it from the free body diagram. So you can consider this to be your example one, a very simple example, okay, from where you can understand the concept of free body diagram. So now let's move on to the next example. Okay, so moving on to the next example. So now let's consider a surface, and then In this surface, okay, pendulum is weight of m, weight of mass m is hanging in this string. Okay, so we have a weight of mass m hanging on this string. So then this is the support, and then we have to uh, make free body diagram, make free body diagram, and then finally write the equation for the force. And if you know, if there is a string and if some mass is attached, then there will be a force which is called tension force. Okay, so the tension which is in the which is experienced by this string is called tension force, and it is always directed towards the support. So here in this direction, there one force will be there which is called tension force, and we all know if there is some mass, uh, it will experience a force in downwards direction, which will be equal to your mg. Okay, and you see there is no force in x direction, and we consider this body to be at equilibrium. Okay, so we consider this body to be at equilibrium, so therefore the net force that is acting on your x direction will be 0, and the net force which is acting on your y direction will also be 0. So x direction we do not have to do anything because we do not see any force acting on the x direction, but for the y direction we can write the equation of force. So here the tension force in up direction and mg is in down direction, so I use a negative sign out here, and we know the summation of fy is 0, which makes T minus mg is 0, or I can write tension force as equals to mass time acceleration due to gravity. Okay, so this will work out as our example number 2. Now, using this kind of example, it is better understood of what a free body diagram means. Okay, it basically means if we have any object, and then to draw all the forces that is acting on that body, and if it is at equilibrium, so then we can write the equation for the forces. Okay, and if it is moving also, we can write the equation for forces, but that we will do later on. Okay, so now let's move on to the next example. So we can create any kind of example we want. Okay, so let's move on to the next example. Here what we are going to take is we are going to just do the extension of our example number 1. So here we have mass m that is resting on the horizontal surface, okay, for which we have already made the free body diagram, but in this case we will consider this body is experiencing a force in this direction also. Okay, some external force, okay, some push in this direction. Okay, and then it is said that this force is making an angle theta with the horizontal. Okay, so now our job will be to make a free body diagram, still considering this body to be at the state of equilibrium. Okay, so the state of equilibrium, so that means there is no acceleration in this body. Okay, so first of all, whatever the knowledge earlier we have, we will use the same thing. So there will be one force which will be acting downwards. This will be your mg, and perpendicular to the surface there will always be a force which is your normal force. So now we know we can resolve the component of the force. If force is making some angle with respect to horizontal, okay, with respect to horizontal, then we know we can resolve this component. If it is making some angle theta, making angle theta, If this is force, then in x or x component, or this will also be theta. So this will be given by f cos theta, and then in y direction, which is perpendicular to f cos theta, so it will be given by your f sine of theta. So the same with the same knowledge, we are going to resolve the component of the force here. So this will be acting in this direction. This angle will be theta. So therefore, the side associated with theta is always given by a cos theta, and the side which is perpendicular to f cos theta is given by your f of sine theta. Okay, so now we have resolved all the components. Only one force was there. We have resolved its components. We have made a free body diagram for this case. So still the body is at equilibrium. So we can consider the summation of force in x direction will be 0, and the summation of the force in y direction will also be 0. Okay, so in x direction, what force you see? So there in x direction, we see one force, which is here f of cos theta. So here this force is in x direction. Okay, so okay, anyways, uh, and we know the summation of fx is 0 since the body is in the state of equilibrium. So f cos theta can be written as 0. This will be our first equation, and the second equation, that is a summation of fy is 0, and from free body diagram, fy is here n is there plus f sine theta. Okay, and then plus not plus, sorry, it will be minus, because you know this n and f sine theta, this n and f sine theta are in the same direction. Okay, same direction, and then this mg is in opposite direction. So therefore, what I am doing, I'm just using a negative sign to uh, represent the opposite direction. So basically n plus uh, f sine theta minus of mg. We know the summation of fy is 0, so therefore n plus f sine theta minus mg will be 0, and n plus f sine theta will be equal to your mg. This will give you an equation, another equation. Okay, so this is how we solve a free body diagram. Okay, and next we will be solving the free body diagram when the mass is kept at the inclined plane. Okay.